What is going on? Mr. Martin here, coming at you for a new unit 6.1. We're going to talk about integer sequences, and in this unit we're going to take a look at different patterns of numbers or objects, and the big bulk of what we're doing is we're talking about sequences. Okay, and then this little term right here, based on its special order, this is something that we want to think about when we look at these sequences. Alright, so let's jump into it. We have a very brief amount of vocab. We have what we call a sequence. This is a list of numbers or objects listed in some special order. Okay, and we're going to do a few different things with sequences. Okay, I also attached this little graphic here. Okay, so the parts of a sequence, there's different vocabulary that you might hear. You might hear the word term, you might hear element, or maybe even member. Okay, but for the most part, term is the one that I'm going to be using all the time. And if we have this sequence given to us here, okay, this would be our first term, and then our second term, our third term, and our fourth term. We read from left to right. Okay, and then we also have this dot dot dot. Okay, and this dot 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 means that something will go on forever. So this sequence, it looks like we are adding 2 to each term. So these are all sequential odd numbers going up. So of course the next one would be 11, then 13, 15, etc. Okay, so that is what that dot 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 means. All right, let's go ahead and check out example number 1. Okay, so we have this sequence here. On your notes, go ahead and put the dot dot dot. I think I forgot to put those on there, so it would be good for us to have those. Okay, and it asks us what are the next 2 numbers in this sequence. Okay, and this is actually similar to that graphic in the previous slide there. We want to know how are we getting from one term to the next. Well, it looks like 1 to 3 could be plus 2. It could also be times 3. But if we did times 3, would we get to 5 from the next? No, we will not. So if we try plus 2, 1 plus 2 gives us 3. Plus 2 also gives us 5. And 5 plus 2 also gives us 7. So this looks like we are adding 2 to the previous term. So our next 2, 7 plus 2 would give us 9, and then we would have 11. Okay, what about example number 2? Are the numbers in this sequence different than the first one? Go ahead and pause the video here, spend a quick little moment to think about it. Alright, welcome back. Hopefully you thought, yes, they are different. It looks like each term is subtracting 2. Okay, to get from 7 to 5, this is actually minus 2, and then 5 to 3, minus 2 again, and 3 to 1, minus 2 again. So what actually differentiates this from the first one? We got the same exact numbers, 1, 3, 5, and 7. We even have the same dot dot dot. Okay, if we look back at the terminology from our objective, what differentiates them is actually the order. Okay, so this one is ordered going from 1, and we are ascending, getting bigger by adding 2. These are the same values, but the order is different. These are going in a reverse order. So this actually makes the sequence very much different. If we wanted the next 2 in this sequence, 1 minus 2 would be -1, and then we would get -3. Okay, so the order does make a difference. This is important for us to understand. All right, next part we have is understanding the notation. Okay, there is going to be 2 different types of notation that I'm going to introduce in this section, and either one that you use will be perfectly okay, but it's important that you understand both of them. So here we have a table. This is the same thing we did previously. Here we just had a list of numbers. This was the first term in our sequence, the second term, the third term, and then the fourth term, and so on. We're doing the exact same thing here. We just have them listed out in a table. So our first term is equal to 1, second term is equal to 2, third term is equal to 4, and so on. So we want to ask ourselves, what are we doing to get from one term to the next? Well, to get from 1 to 2, we could either add 1, right? But if we add 1 to 2, would we get 4? No. What about if we multiply by 2? 1 times 2 is 2. Then 2 times 2 is 4. 4 times 2 is 8. Yep, it looks like we are multiplying by 2. Okay, so I'm just going to draw these here. You guys might want to draw those in too. That way when you look at your notes, you have a nice representation of what is going on. So to fill in these empty 2 boxes, we got 16 times 2. That gives us 32, and then 32 times 2 gives us 64. Okay. So one thing I want to talk about, I have some sections here that I'm going to reveal to you. Let's go ahead and reveal the first piece. We have what we call a sequence name. Okay, if we look at the subscript table, okay, this is one of our types of notation that we're going to use, and any of these letters can be used. In our case right here for this example, the sequence name is A. Okay, and I have something on here also that we'll see here in a minute, but we're not limited just to A. It could be any variable that we want, but just in this case we are using A. So down here in your notes, I do want you to write this, okay, and we're going to talk about this a little bit more, but just the way that we say the notation, okay. If we have, you know, the big text and then we got the small text written a little bit below to the text on the left, this is what we call subscript. This is down below. You know, if we had exponents, that is what we call superscript. If it is down below, we call it subscript. So this is our subscript notation, subscript. Okay, and it's important how we actually say this. This is pronounced A sub n. So A sub n. So if we were looking at this first term, this would be A sub 1, then we got A sub 2, A sub 3, and so on. So we want to know that subscript is A sub n. Okay, we also have function notation that we can use, and it looks like this. Okay, and this would be our function notation. Function notation. Okay, and the way that this is pronounced, we would say A and then the word of. So this is going to be A of n. So you're either going to have A sub n for subscript or A of n for function notation. Okay, let's talk a little bit about subscript. This table here is the same table here, so we can go ahead and just fill in this blank part of the table. And A sub 7 is 64. Okay, so when we describe using subscript or function notation, like I said before, A sub 1 is equal to 1. So if we were looking for A sub 6, which was our first blank spot, we would say A sub 6 is equal to 32, or we could say A of 6 is equal to 32. So these will mean the exact same thing. They are both okay depending on which one you want to use. I am more of a subscript guy. I think it looks cool, and plus we're going to use function notation later on for some other stuff, so it's kind of fun to use this while we're in this section. Okay, so the other thing that is important to know, and we saw a little bit of this right here on the left, when we say A sub n, okay, this n lets us know that we have an unknown term. So here we have A sub 7, but what if we wanted the 32nd term or the 55th term? If we are asking for an unknown term, okay, we can use that variable n with our sequence name. So A sub n is our unknown term, and this is going to be helpful to us once we start writing some formulas. Okay, and like the A of 6 and A sub 6, different notation is okay. These mean the same thing, so A sub n is going to be the same thing as A of n. And like I said earlier, we can use, oops, let me just go ahead and delete that. Like I said earlier, we can use a other letters to name our sequence. So some that you might see pretty commonly is F. You know, here we got f of 1. F is a big function variable that is used widespread. Okay, so as long as we have a sequence name, we can find our sequence terms. Okay, and then the other part that is important to us is listing these things as ordered pairs. Remember when we had our tables before, when we did graphing linear equations, we had our XY table. It is going to be the same thing here. We have the sequence term number, and then we have what the actual term number is. So this is like our XY table in our ordered pair. This is going to be our n, and then this is going to be our unknown term right here, a of n, with our ordered pair n comma a of n. So this is very important to know. So keep this little box handy. Continue to look at this, please. Kind of commit this little section to memory and how to say this vocabulary here, a sub n and a of n. All right, let's go ahead and jump into example number 3. We actually have a graph here with some plotted points. Okay, so remember the x value, we said that was n, and then our y value is going to be our a of n. Okay, so if we are looking at the first terms of our sequence, our first dot starts down here. This is term number 1. Okay, so that is our n. Remember, x values were independent, y values were dependent. They were considered the output. So if I said 1, what would be my output, my y value? That would be 0. So my first term here is going to be 0. My second term jumps up to 3. My third term is here at 6. My fourth term is here at 9. Okay, and then we are looking for the first 6, so we got to kind of figure out what is this pattern telling us. How are we going from one term to the next? You guys are all super bright. I know you already see it. So we are adding 3 from one term to the next. So my next 3 are going to be 12, 15, and 18. All right, here it is asking what is f sub 10. So we're looking for the 10th term in the sequence. Here we have the first 6. Okay. Oh, whoops. I gave you 7. Let's erase that for now. 1, 2, 3, 4, 5, 6. Okay, so here we got the first 6. Okay. If we are looking for the 10th, we can do one of two things. We can just write out the next 4. Okay, so that would be 18, 21, 24, and 27. Okay, so that's not so bad since it's only 4 more. But what if I was asking for what is f sub 38? Okay, we might not want to write all of those out. So I want us to think about this mathematically. If we had that 6th term, okay, and we know that we're looking for the 10th term, we want to ask ourselves, how many more terms are we looking for? We're looking for 4 more terms. And if we're adding 3 each time, how many would we need to add if we're looking for 4 more terms? This would be, you know, plus 3, plus 3, plus 3, and plus 3. So how could we figure that out in our head? Well, if we know we got 4 plus 3's, that is the same as 4 times 3. And 4 times 3 would be 12. And then we would simply add that to our last term. 15 plus 12 gives us that 27. So that is one way that we can look at finding that requested term there. So let's go ahead and do that method for f sub 15. If we have the 10th sequence term and we are looking for the 15th, we need 5 more terms. 5 more terms at plus 3 is going to be 15. 15 plus 27 is going to give me 42. All right, very good. So let's now describe how we go from one term to the next using complete sentences. Actually, I'm going to pull this down. I'm going to have you guys pause the video, write down what you think, and then come back and take a look. All right, welcome back. So going from one term to the next, 3 was added. Not too difficult. Describing how the graph changes. So what is the graph actually doing? Okay, so here we actually have a rate of change that has a constant increase of 3. For every term that we go up, we are increasing by 3. And that word constant, if you remember from previous lessons, if we have a constant rate of change, then we have a linear graph. It looks like it is a straight line right there. All right, our next example, it wants us to consider the following sequence. We got 1, 4, 16, 64, and 256. What does it look like we are doing from one term to the next? It looks like we are multiplying by 4. So how would we describe this? From one term to the next, there is a multiplication of 4, or you could say we are multiplying by 4. All right, so if we are looking for the 8th term, okay, so I do want to show you something on the calculator here. Let me pull that up real quick. All right, I went ahead and got my calculator up. I reset it. I am good to go. So there are some neat functionalities on this calculator that will help you save some keystrokes. So it looks like we're multiplying by 4. We already know that. So if we have the 1, 2, 3, 4, 5th term here, oops, 5th term is 256. Okay, so if we type in 256, we are looking for the 8th term. So we need to find the 6th, the 7th, and the 8th. So we're going to multiply by 4. Okay, that's going to give me the 6th term right here. So instead of retyping this 1024, I can simply hit the multiply button again. It's going to give me the previous answer, and then I'm going to multiply that by 4. That is my 7th term, and then I'm going to do that one more time, and I am going to get my 8th term. So if we take a look here, is that correct? 16,384. That is what I got. So that is correct. So let's think about this. If I am multiplying by 4, then multiplying by 4, then multiplying by 4, how could I do that in one simple keystroke? Well, I will show you right here. 4 times 4 times 4, right? Well, 4 times 4 is 4 squared. If we do it a third time, that is actually 4 to the third power, or 4 cubed. So if we do times 4, this little button above the division symbol is our caret. That brings us up to our exponent, and we know that we are looking for 3 more terms. And then we hit enter, and that gives us that exact same answer of 16,384. So let's look for B of 10. We know that 256 was our 5th term. We know we're multiplying by 4. We know we need the caret. Okay, and how many more terms are we looking for? If we have 5, we need 10. We're looking for 5 more. So we do it to the 5th power. That's going to give us 262,144. Let's see if that is correct. That is correct. All right, so go ahead, pause the video here. I want you to graph these out. It tells us to graph the terms. All right, welcome back. Boom, I got my graph right here. So it looks like it went up a little, went up even more, went up even more, and then just jumped up a crazy amount. So how could we describe this? I would say something like the graph's rate of change increases drastically from one term to the next. Now, it's not so drastic in the beginning, but after those first few initial steps, it's going to get more and more drastic. Look at what happened from 8 to 10. We went up well over 200,000. Okay, so it is going to be very drastic. And if you haven't guessed already, the type of graph this is an exponential graph. Okay, so we're going to be dealing with exponential functions pretty soon here. All right, very good. And my last example, we have this little graphic here. It looks like we got 1 dot, and then now we got 4 dots, and then it looks like it's just starting to create these bigger squares. So we went from 1 dot to 4 dots to 9 dots to 16. Let's see, maybe if I add 3, can I add 3 again? 4 plus 3 would give me 7. Nope. 4 plus what would give me 9? Maybe 5. And then 9 plus 7 gives me 16. Oh, looks like we got a nice consistent pattern here. Okay. So how would we describe going from one term to the next? I said something like this. From one term to the next, we are increasing amounts by sequential odd numbers were added. Okay, so we went 3, then plus 5, plus 7, plus 9. This is actually, if you haven't noticed already, these are a perfect square sequence. Okay, perfect squares. What is 1 times 1 squared? That's going to give me 1. 2 squared, that's going to give me 4. 3 squared, that's going to give me 9, and so on. So these are our perfect squares, hence the shape of these dots. So if we know that these are perfect squares, the first term is 1, the second term is 4, and so on. What would be our sixth term if this is a perfect square? Well, 6 times 6 would be 36. Okay, and our seventh term, a sub 7, that would be 49. So go ahead, pause the video, graph yours. I'm going to graph mine real quick. All right, so it looks like we got this nice little curve going. So how is this graph changing? Well, it is having a rate of change that just slightly increases from one term to the next. It is not constant like the first graph we had that was linear. Our second one increased it so drastically, and that was our exponential. This one is just a little bit of a slight increase. It's a little bit more than the constant, but a little bit less than the exponential. And if you haven't recognized the shape, some of you guys out there might know what these are called already, but if you don't, that is okay. This is what we call a quadratic, okay, and this is where we have a curve of some sort like this. All right, so that is it for this lesson. I truly hope you enjoyed it. Smash that like button down below. You know what to do. Please go ahead and get that coursework completed. Prepare for that mastery check. You know it is coming. Go ask for help if you need it. Ask a friend, ask a foe, anyone you know. It is okay. You are good to go. All right, I will catch you on the next one. Peace out.